Let me define the residuals. So just before I do, let's remind ourselves that y hat is x transpose x inverse, x transpose y, or x beta hat. The residuals are then defined as E, which is y minus y hat. That's y minus the hat matrix times the y vector again. If I factor out y, I get I minus x transpose x inverse, x transpose times y. The residuals are orthogonal to any linear combination of the columns of x, including x itself, any specific column of x, and y hat. Here's why. And we'll show you the intuition behind this in a minute. So to be orthogonal, we would have to show that E transpose times any linear combination of the x's, xl in this case, would be 0. So here's E transpose, I'm missing a y there, a y transpose there. E transpose is this, y times I minus x transpose x inverse x transpose, and then times this guy right here, which is xl. If I bring the x in, I get an x right there, and then an x right there because of x times I. That works out. This cancels with that. These two are the same, so you get 0. So for example, if L is x transpose x inverse, x transpose y, or beta hat, then we multiply x times beta hat or get y hat. We see that the residuals are orthogonal to y hat. In addition, L could grab any specific column of x. It could just be, L could just be a collection of zeros, a 1, and a collection of zeros, and then multiplication of x on the right by this vector would grab that specific column. So in other words, the residuals are orthogonal to any specific column of x. A consequence of this is if x contains an intercept, one of its columns is a 1, which means E transpose times Jn is 0, which means the residuals sum to 0. And again, of course, the residuals inner product with any column of x is 0. Here's why this is the case. Let's draw the picture out. So our y, here we're drawing in R3, so n is 3 and y is a point in R3. Y hat, the P, the plane that is defined by the column space of x, is the plane that we'd like to project y onto. That projection is this orthogonal projection onto the plane, the space of linear combinations of the columns of x. That yields y hat. The residual, here I just redrew it over here, is exactly that orthogonal line. Notice if I move this line anywhere, it's going to be still orthogonal to the plane defined by x beta, and that's why the residuals they're orthogonal to the plane everywhere, and that's basically what's giving us this result. Remember, the residuals are y minus y hat, and our least squares criteria was to find the y hat that's a linear common that lives in that plane that minimizes the sum of the squared distances. So our least squares criteria can just be seen as summing this, minimizing the sum of the squared residuals. Let me talk about another point about residuals. Let me let x tilde be our x design matrix that we were talking about, plus another k columns. So in this case, the plane defined by the space of points in Rn such that they are equal to x tilde times gamma for some gamma in R p plus k, that space has to contain the plane of vectors in Rn that are equal to x beta for beta in Rp. Why? Because if we were to take the vectors gamma such that the latter k columns are all zeros, then we simply get this whole space P as a special case. So P tilde when we add columns to x, we make the plane that we're trying to project on bigger. We're adding dimensions to it. So if in our picture where y is a point in R3, if our x is simply a single vector, then we're trying to project on a line. If we add another column, then that line turns into a plane, and that plane of course contains that first line as a special case. So in other words, the fitted values where the y-hats exist in this larger plane has to be, the least squares has to be, I'm forgetting my square there, but it doesn't matter, has to be less than or equal to the least squares where y is in this smaller plane. So in other words, if you add columns to your x, your y-hat must get closer to y. And then the sum of the norm of the e tilde values, the ones from projecting onto this plane, must be smaller than the norm or the least squares criteria for projecting onto the smaller plane. Notice if x is n by n of rank n, then the whole space, this plane, is nothing other than a reorganization of the space. It's just a different set of axes. The axes now defined by x. So we haven't changed anything. We should be able to perfectly fit any point in Rn because we can, that's the definition of the matrix being of rank n, x being of rank n. So that in that case, y hat has to equal y and our residuals have to be 0. In other words, if we add enough terms to our design matrix, then you're going to get perfect fit.